Channel on KStars Ekos focusing. This video is going to be all about focusing using Fourier Power. So it's going to be all about what it is and how you might use it. So it's going to start off with a little bit of theory. So the underlying theory to all of this is a paper by these two guys, Tan and Schultz, that was published in the Royal Astronomical Society's journal, a Fourier method for the determination of focus for telescopes with stars. So I don't have access to this journal, but there is a preprint in archive of the same paper. So I'll put a link in the video description, so for those of you that would like to, you can have a look at the paper yourselves. So I think the basis of this is that these guys noticed that some properties of Fourier transforms could be used as a method for focusing. So I'm not going to go through Fourier transforms per se, because there's an awful lot of information available on the web for those of you that may not be familiar with them. But I'll say a few things about them and go through the properties of Fourier transforms that these guys use in their paper to help with focusing. So I suppose the first thing to say about Fourier transforms are that they'll transform a signal, be it a wave of some form, or something like a picture, like a focus frame, into Fourier space, which you can think of as an infinite collection of sine waves, each with an appropriate amplitude and phase that would replicate the original signal. So the information in Fourier space is the same as the original information. It's simply transformed into a different way of looking at it, and this facilitates some interesting properties that can be used for various things, and in this case to help with focus. So a few pages down in this paper is a couple of graphs that really give the essence of these guys' approach. So what the graph on the left is showing is a series of three different Gaussians, and then on the right are the Fourier transforms of the same Gaussians. So the first thing to be aware of is that a Gaussian transforms to another Gaussian in Fourier space. Again, you can Google mathematical proofs of that if you're interested. But the thing to notice, and this is key to the theory that these guys developed, is that a narrow Gaussian, so in this case this sort of orange, very sharp peaked Gaussian, transforms to a wider Gaussian in Fourier space, which is this line here, and a broader Gaussian in, let's call it picture space, which is this sort of yellow curve here, transforms into a very sharp Gaussian in Fourier space. So this is kind of part of a broader theory called the uncertainty principle, which is that Fourier transform pairs can't be known, or both values can't be known exactly, and the tighter you know one value in one space means that the less accurately you will know its Fourier transform. So very well known and well defined sharp peaks transform into less well known and much broader peaks. So that's probably best known in quantum mechanics, with position and momentum being Fourier transforms of each other. So the more you know, or the more accurately you know the position of something, the less accurately you know the momentum, and that's the nub of Heisenberg's uncertainty principle. But back to focus, this sort of idea that if you had a very sharp Gaussian, which obviously would represent an in-focus star, you would end up with a very wide Gaussian in Fourier space, and conversely an out-of-focus wide Gaussian in a focus frame would transform into a very narrow and sharp Gaussian in Fourier space. So that's fine, but how does that help us with focus? So what you can do once you've got this graph is you can see if you were to calculate the area under this graph, you would see that for the very wide Gaussians in Fourier space, you would end up with a larger area. So that means that as you get nearer and nearer to focus, so in picture space, your stars get tighter and tighter as you get nearer to focus. Over in Fourier space, you have a progressively wider and wider Gaussian, and were you to calculate the area under that graph, you will get a bigger and bigger number. Now, the area under the graph is in effect the energy in Fourier space, but obviously the energy coming into a focus frame is time bound. You might take a 1 or 2 or 5 second sub exposure. So the energy here really is power, because it's energy associated with that 1 or 2 or 5 second exposure. So by calculating the area under the graph, what you're really calculating is the Fourier power, which is why this focus method's called Fourier power. So that's fine. So you can imagine a focus frame consists of a series of stars and noise. So the other important concept is that if you assume that the noise in the focus frame is white noise, then the Fourier transform of that would be a constant power at all frequencies Fourier transform. So what these guys, Tan and Schultz, in their paper recommend is you can go to a part of the Fourier transform where you're fairly sure there won't be any star contributions, measure the power contribution at that value, and that will be the contribution from the white noise, and then you can subtract that from all of the frequencies within Fourier space, and that can give you a good approximation or a good value for the power for that focus frame. The way I implemented it was slightly different. I background subtracted the focus frame before taking the Fourier transforms, which kind of is the same thing. I found I got a slightly better result from doing that, but in essence it should be the same thing, which is that the contributions to power that I look at in the focus frame is really just that's coming from the stars. Well, that's the theory. So going back to KStars, the way you would run this in Ekos is you know, you set everything up as you normally would if you're using, for instance, HFR, except you would go to the measure drop down and select Fourier. Now, one thing that will happen is this use weights checkbox gets grayed out because there's no real way of estimating the weighting of a particular data point using Fourier, so it doesn't make sense to enable that. So all you need to do, select Fourier and run autofocus. Notice that the y-axis on the v-curve changes to Fourier Power. Other than that, everything should be fairly familiar. The focus system will still calculate the HFRs for you, although the HFRs are not used by the Fourier Power calculation. It will, as I was saying earlier, produce a maximum rather than a minimum. This particular run's not the greatest. You know, it's given a fairly poor value of the R squared. I might just run it again whilst I talk about things. But other than that, the focus run will be pretty much as you would expect from any of the other measures. So I think it might be worth just giving it a go. I mean, personally, I've not found this to be better than HFR, but you know, by all means, give it a go and you know, see what results you get with it. I guess an obvious question is, well, how does this deal with donuts? Now, in the paper by Tan and Schultz, they say you do need to be careful not to go too far out of focus if you have a scope with a central obstruction, because the donuts might mess with the algorithm in the same way as they mess with the HFR algorithm. So, you know, I'm not sure this is going to help greatly with you know, folks that do have scopes with central obstructions, but you know, by all means, give it a go and see what sort of results you get. Be interested to know. The guys in their paper, Tan and Schultz, reckon that this for them is more accurate than using HFR. They've tried this on both amateur scopes and professional scopes, and you know, they seem pretty positive about it. So you know, it's definitely worth a look. This particular run, as you can see, was slightly better than the last one. Not quite sure what happened on the last one, but yeah, by all means, you know, give it a go and you know, let me know how it goes. So clear skies, catch you next time.